It's your boy Dappa, running with Dappa, day 25, y'all. We'll be making progress. Alright, cool. Today's indoors. Check out the fit. Jamaica shirts. Vesty shoes today. Cricket shirt. No laptop, no headphone. I'll be chilling while I'm on my laptop today. Alright. Using my phone to record and see how that goes. No GoPro today, man. But we outside. No, we're inside. Alright. It's alright.
So the first algorithm I want to cover is Kadane's algorithm. I'm actually not sure how it's pronounced because I've only ever seen it written before, but it's named after a person. And while this algorithm is definitely not a hard algorithm, especially compared to the other algorithms we're going to look at in this course, it's such a fundamental and important algorithm because there's so many things that we can learn from it. And that's really what I'm going to be focusing on. This algorithm has a lot of overlap with a lot of other algorithms that we're going to look at in this course, particularly two pointers and sliding window. And it's also technically a dynamic programming and greedy algorithm. The problem is that we're given an array of integers. They could be positive or they could be negative. And in this case, we want to return a non-empty subarray from this entire array that has the largest sum possible. Now, what if we actually had all negative values? What if all of these were negative? What would the answer in that case be? Would we just return an empty array? Well, first of all, we're going to return the largest sum. We're not actually returning the subarray itself. We're returning the sum. But what would the largest sum in this case be? Would we just say 0? Well, this variation, we are looking for a non-empty subarray. So if we had all negative numbers, we can't return 0. We would just return the value that is the largest. It's still a negative value, but it's the largest. So we would, in this case, return -1. That would be the largest sum. If we try to make the subarray any bigger, then our number is just going to become even more negative. And we're trying to get the largest sum, even if it happens to be a negative number. And just to clarify, when we say subarray, that's by definition a contiguous subarray. This does not count as a subarray. It has to be contiguous. We can't just have a hole like that. So now that we actually understand the problem, let's try to look at some solutions. When you can't come up with a solution, the easiest thing to do is think of the brute force solution. To find the subarray with the largest sum, let's just go through every single possible subarray and keep track of what the largest sum we calculated was. And then once we've gone through every single subarray, we can return that result. And the way to do that is basically get every single subarray starting at the first position. So this is one subarray, this is another subarray, this is another subarray, and keep doing that, starting at this first position, and keep track of the sum. To get every subarray starting at the first position is going to be O of n, where n is the size of the array, and then to do the same exact thing starting at the second position, it would also be big O of n. And we, of course, would have to do that starting at every single position in the array, so the time complexity is going to be n times n, which is going to be n squared. The code for that would look something like this. Not super fancy. We're given an input array nums, which is this in this case. We keep track of what the max sum is so far. Now, I initialize that to be the first element, because remember, we can't have a non-empty subarray. If we could have an empty subarray, the sum of an empty subarray is 0, so that's what I would initialize the max sum to. But in this case, we can't, so I'm just taking some arbitrary subarray. In this case, the simplest thing to do is just take the first element and assign it to the max sum. Sometimes people will also set this to a default value of, let's say, -infinity, or whatever the minimum integer is in the language that you're using. We would set it to a really negative number because we're trying to find the max. So the first element we would look at in the array would end up being larger than -infinity, and then max sum would end up getting reassigned at that point. Also, it's worth mentioning, in this case, I'm assuming that the input array is non-empty. If it was empty, we would not be able to do this. In that case, we would immediately return or maybe throw an exception because our goal is to find a non-empty subarray. If we're given an empty subarray, that would be impossible. These are just some edge cases that I think can sometimes be important when you're discussing things with your interviewer. But back to the algorithm, essentially we're going to have two pointers. I is going to be the starting pointer, so starting at this position with our I pointer, and J would then also start here, and then J would be moved to every other position, and I and J basically determine that this is a subarray. We would keep track, as we keep adding another I value, we would keep track of what was our sum so far. That's going to be our current sum. Initially it would be set to 0, but J would start here, then our sum would be 4, we'd add this value, then our sum would be 4 minus 1, which is 3, and we would keep doing that. And then by the time we got to the end, we would have the entire sum, and then our inner loop would be finished, and then our I pointer would finally be shifted over here, and then we would have a J pointer that would go through the entire array. So at every single subarray, suppose this one, we're going to have a current sum. If at any point the current sum becomes greater than our max sum, we're going to reassign max sum. An easy way to do that in code is just take the maximum of these 2, and then assign it to max sum. Remember, we don't actually care about the subarray itself, we just care about what the max sum of it happens to be, and then at the end, that's what we're going to return. So this is a working solution, but the time complexity is n squared. The question is, can we do better? And we definitely can, but the question is how. Is there any repeated work that we're doing here, or any redundant work that we're doing here? And the answer is yes. Let's take a deeper look. Just looking at this subarray, our sum would be 4. We're trying to get the largest sum, so a positive number, no matter how small it is good because it's contributing. It's making our sum larger. Negative numbers, on the other hand, do the opposite. They make our sum smaller. So we had a 4. Now if we make our subarray a little bit bigger, now we have 4 minus 1. That's a sum of 3. That's not good, but from the perspective of this 2, the 2 doesn't know what came before it. As far as it's concerned, there weren't 2 values that came before it. As far as this guy is concerned, there was just a single 3 over here. It makes no difference to this guy, but we're pretty happy when we're over here because this is a positive number, and the sum of all values that came before were also positive. It was 3, so 3 plus 2 is going to be 5. So now our sum at this point is 5. Now before we continue through the rest of this array, let's just focus on this. What's the max subarray sum of this array? It is definitely 5 because we take the 4 and the 2, but we have to subtract 1. It would be nice if we could just ignore this value, but remember, a subarray is by definition contiguous. So if we decided to not include this -1, we would also have to forfeit the positive 4, and then we would have a subarray sum of 2. Or we could do it the other way. We could forfeit this guy, and we would only have a subarray sum of 4. It's worth including this -1 because by including it, we can add a positive 2, which counteracts this guy, but also gives us 1 value extra. So it's worth it to include this. This idea is going to be extended now that we get to the next value over here. So we know the max subarray sum of this is positive 5. By the time we get here, we don't care if it's 3 values or 1 value or 2 values. We can pretend like these don't even exist. There's a positive 5 before the -7, so we can add these 2 values, and that will give us a sum of -2. Now, -2 is definitely not the max subarray sum of these 4 values so far. As we keep track of our max sum, it would still be set to positive 5. But the -2 is still important because it's going to be our current sum. The reason we have a current sum and also a max sum is because for the current sum, that is the sum that we can add to the next value as we go through the array. So this -2 will be added to the positive 3, or at least we're allowed to do that. We don't necessarily have to, and we can add it to the positive 3 because we know that this sum applies to the subarray that ends at this value. So whether it's just this itself, or maybe 2 values or 3 values, it doesn't matter. We know that that subarray includes this guy, so if we take this subarray, add it to this value, they are still contiguous. That's the important thing here. But now, my question for you is, we know we don't care about these values anymore. There's a -2 that came before the positive 3. We're allowed to add this to the positive 3, but we don't have to. And I just have one simple question for you. Why would we ever add a negative value if we don't have to? A negative value is never going to increase our sum. We're looking for the largest sum, so if we have a choice, we should never add a negative value, a negative previous sum, to our current value. And this algorithm is really that simple. So now that we have a choice, we're going to say that the current sum, which basically means the largest subarray sum ending at this value, it's either 3 or it's 3 minus 2, which would be positive 1. We're of course going to choose the larger value, so we're going to say, forget about this. The largest subarray sum ending here is positive 3. And then we would go to the next value here. By the time we get here, we don't care about all these anymore. We know that the largest subarray sum ending at this value was a positive 3. So we have a choice. We can take this value by itself, or we can say 4 plus whatever the current sum before was. And since our previous current sum was positive, we are going to add these together. So our current sum by the end would be a 3 plus 4, which is equal to 7. And our previous max sum, if you recall, was 5. So at this point, 7 is greater than 5. So our max sum is going to be assigned to 7 now. And that would happen with this line of code. So the code for what I just talked about would look like this. This is the algorithm that we're interested in. It is a linear time algorithm. We don't need nested loops. Now this can make it a little bit confusing exactly what's going on because we're not even keeping track of pointers anymore like we were earlier. But implicitly, we still do have a window that we're looking at. It's just not obvious that that's what we're doing here. So we're initializing our max sum the exact same way. We're also keeping track of a current sum. So suppose our window is initially like this, where we go through every number in the input. We first start at the first number. Before we add this value to our current sum, we want to make sure our current sum isn't negative for the reasons I talked about a bit ago, because we have a choice. We don't have to include any values that came before this value. And we would definitely not want to do that if the previous current sum was negative, because that's never going to increase our sum. So basically with this line of code, we're ensuring that our current sum is never negative. And then after we do that, we can take n and add it to the current sum. Now these two lines of code could be condensed into a single line. I encourage you to do that on your own. And if you're not sure how, feel free to ask in the Discord server. So at this point, our current sum would be positive 4. And then we would possibly update the max sum. Initially, our max sum was also set to 4 just as a default value, so at this point our max sum would stay as 4. Next though, we would get to the next value, a -1. Our current sum is not negative, so it's going to stay as 4, and then we're going to add n to our current sum. We're adding the -1 to our current sum. So at this point, our current sum would be 3. It got smaller, so our max sum would not be updated. Our max sum would stay as 4, but our current sum got smaller. Isn't that a bad thing? Well, yes it is, but we had no choice here. We could have either had this as our current sum, which is 3, or we could have had this as our current sum, which is -1. Of course, 3 is bigger than -1. But why not just set it back to 0? Well, by the time we get to this 2, we have some more choices. We know that the max subarray sum from here was 3, so we could say the max subarray sum ending here is equal to 5 by adding that 3, or we could leave it as 2. Of course, we're going to add the 3. We do have to add a -1, but it can't be helped. We're sacrificing that to gain this. So at this point, our current sum would be 5, and our max sum would also be updated to 5. Next, we would get to -7. So we would take our current sum and add -7 to it, so that would give us a -2. So now our current sum has become negative. We definitely don't like that. Our max sum is going to stay as 5 so far. Then we get to 3. Our current sum is negative, so we're going to reset it back to 0. At this point, we know that nothing that came before is going to help us. We would love to be able to include the +4 and the +2, but to do that, we have to sacrifice a -7 and a -1. Never mind the -1, the -7 is enough for us to be convinced that we shouldn't try to include these two values, because the -7 is going to outweigh those anyway. So we just forget that any of these ever existed. We have a 3 so far. It's not bigger than our max sum, which was 5, but we can continue. Now our current sum is going to be 3. Then we get to the next value. Our current sum is 3. We're going to add 4 to it. Now our current sum is 7. That's bigger than our max sum, which was 5. So now this is our max sum, and we went through every single value. We got to the end of the array, so we end up returning 7. This is an algorithm that's deceptively difficult. When you look at it like this, it just seems so simple and trivial. But this algorithm definitely has some complexity behind it. And if you were paying attention, you might have noticed that we were using a 2-pointer technique. Well, definitely not from this code, but our 2 pointers essentially represent what the subarray is. We can also call that subarray a window. Kadane's algorithm has a lot of overlap with another popular algorithm called the sliding window algorithm. Well, technically it's more of a pattern than an algorithm. It's a category of problems, and before we finish, I want to show you the sliding window variation of Kadane's algorithm, and we're going to go more in detail later on, but I think this will be a good introduction. What if we slightly change the problem? We were looking for the max subarray with the largest sum, and we were trying to return the sum itself. But what if we're actually trying to return the indexes of the subarray, the beginning and the end index, aka the left and the right index of that subarray? Well, the algorithm would be very, very similar, but in this case, we would use the sliding window technique, which is also based on 2 pointers. The idea is that we're going to have 2 pointers. I like to call them the left and right pointer, and I use a capital L in my code. I used to use a lowercase l, but then a lowercase l looks very similar to the 1, so now I use capital just to make it very clear that this is a variable, not an integer 1. And with these pointers, the left pointer is called the left pointer because it will always be on the left side of the right pointer. In this case, though, the left and right pointer can be equal. They can be at the same position. That's perfectly fine because that just means we have a subarray of length 1. But our left pointer should never cross the right pointer. And with that as our main restriction, we get the sliding window, which is basically a window that, potentially is shifted to the right. It can also grow in size. So the way we saw Kadane's algorithm run initially was that this was our max subarray sum. Then this was our max subarray sum ending at this position. Then this was the max subarray sum ending at this position. So you can see our window is not technically sliding, it's mostly just growing, but it still counts as the sliding window. And next, the max subarray sum ending at this position was this window. And then finally, when we got to this point where we were looking for the max subarray sum ending at this, now I use capital just to make it very clear that this is a variable, not an integer 1. And with these pointers, the left pointer is called the left pointer because it will always be on the left side of the right pointer. In this case, though, the left and right pointer can be equal. They can be at the same position. That's perfectly fine because that just means we have a subarray of length 1. But our left pointer should never cross the right pointer. And with that as our main restriction, we get the sliding window, which is basically a window that, potentially is shifted to the right. It can also grow in size. So the way we saw Kadane's algorithm run initially was that this was our max subarray sum. Then this was our max subarray sum ending at this position. Then this was the max subarray sum ending at this position. So you can see our window of the right pointer. In this case, though, the left and right pointer can be equal. They can be indexes of the subarray, the category of problems. And before we finish, I want to show you the sliding window variation of Kadane's algorithm. And we're going to go more in detail later on, but I think this will be a good introduction. What if we slightly change the problem? We were looking for the max subarray with the largest sum, and we were trying to return the sum itself. But what if we're actually trying to return the indexes of the subarray, the beginning and the end index, aka the left and the right index of that subarray? Well, the algorithm would be very, very similar, but in this case, we would use the sliding window technique, which is also based on 2 pointers. The idea is that we're going to have 2 pointers. I like to call them the left and right pointer, and I use a capital L in my code. I used to use a lowercase l, but then a lowercase l looks very similar to the 1. So now I use capital just to make it very clear that this is a variable, not an integer 1. And with these pointers, the left pointer is called the left pointer because it will always be on the left side of the right pointer. In this case, though, the left and right pointer can be equal. They can be at the same position. That's perfectly fine because that just means we have a subarray of length 1. But our left pointer should never cross the right pointer. And with that as our main restriction, we get the sliding window, which is basically a window that, potentially is shifted to the right. It can also grow in size. So the way we saw Cadane's algorithm run initially was that this was our max subarray sum. Then this was our max subarray sum ending at this position. Then this was the max subarray sum ending at this position. So you can see our window is not technically sliding, it's mostly just growing, but it still counts as the sliding window. And next, the max subarray sum ending at this position was this window. And then finally, when we got to this point where we were looking for the max subarray sum ending at this position, we had to slide our window from this to now be this. So our window went from this to now this. And at this point, our left and right pointers would both be over here. And then when we got to the next value, our window actually grew. So it's a sliding window. We have some window of values that we care about. We care about all the values that are inside that window. In this case, all the values inside that window represent our current sum, which is not necessarily the same as the max sum. So in terms of code, it's pretty similar. We initialize our max sum the same way. We initialize the current sum the same way. We initialize our result pointers, which I call the max left and max right. These represent the positions of the window with the max sum. And we initialize our left pointer to be here. And we could also initialize our right pointer to also be 0, but I don't do that because we're iterating our right pointer through the entire array. So our left is here, our right is here. We check the same thing we did earlier. If our current sum is less than 0, we're going to reset it back to 0. But before we did that with one line because we could, but in this case we can't do it with one line because if our current sum is less than 0, we also have to reset our left pointer. In this case, our current sum is not less than 0, it's equal to 0. So then we add the value here to our current sum. So now it's 4. Is our current sum greater than the max sum? Yes, it is. So we're going to set our max sum now equal to 4. And this is the important part. We also have to update our max left and max right. So we're saying here that our pointers are 0, 0. That this window, which is representing this subarray, is the one that contains the max sum. So then we would set our right pointer here. This would be the current sum. It's not bigger than the max sum. Then we would update the right pointer to be here. Then 5 would be the current sum. It is greater than the max sum, so we would update the max sum. We would also say that 0 and 2 are the pointers that represent the max sum. Then we would move our right pointer here. This is negative 2, so it's not the max sum. Then we would move the right pointer here. At this point, our current sum was negative. It's negative 2, so we would set the current sum back to 0, but we would also take that left pointer, which is all the way over here still, and we would move it to be where the right pointer is. That's essentially us saying that we don't care about all the previous values because they summed up to a negative value, and we don't want to consider that anymore. We want a fresh start. So we update the pointers like this, and then we would end up shifting our right pointer over here, and then we would find that 7 is the max sum, and the left and right pointers that give us that are, I think this is 4, and this is index 5, so that's what we would end up returning. Now this was a lot to take in because Cadane's algorithm just has a lot of depth to it. It overlaps a lot with some other really important algorithms, including two pointers, sliding window, greedy, and dynamic programming. But once the concepts sink in, it really makes a lot of sense. It's an efficient algorithm and definitely one worth learning. Now let's take a deeper look at the sliding window algorithm, looking at a simple variation where the window is of a fixed size. Suppose we're given an array and we want to return true if there are two elements within a window of size k that are equal. And within a window of size k basically means that the window can be at most of length k. And the two elements have to be different elements, so we can't just say that this window has two elements that are the same because they're not two different elements, because it's just the same position. They have to be in different positions. Now suppose our k is 2. What would the answer be for this example array, and how would we determine the answer? Well, the brute force would be to look at every window of size k. So this is one window. Are these two values the same? Nope. This is another window. Are these two values the same? Nope. This is another window. Are these two values the same? Nope. Only if our window could have been of size 3 instead of 2, because then we would be able to have considered this window, and we know, while these are not the same and these are not the same, these two are the same. But we can only have windows of size 2, so this doesn't work. We try the next window. These two are again not the same, but finally when we get to the end, this is our last window, these two values are the same. So brute forcing this is not too difficult. It might not be clear with a window of size 2 exactly what we would do, because with a window of size 2, we can just take the two elements and just check if they are equal. But of a variable window length that's even bigger, suppose 3, how would we do this and this and this? Well, we would do something like this, where our left pointer would represent the beginning of our window, and our right pointer in this case should never be at the same position as our left pointer, because then in that case we might compare these two and say that we found equal values, but they're not two different values. And let's say in this example our window is of size 3, 3 just to illustrate the entire algorithm. So in this case, our right pointer is always going to be initialized to left plus 1, because we know our window is of size 3, but here we're checking for duplicates. We're going to check, is this left value equal to any of these other values in this window? And to do that, we're going to have a right pointer. So here our right pointer is going to be at this position. We're going to check, are these two equal? Nope. And then we're going to increment our right pointer here. Are these two equal? Nope. Well, we've gotten to the end of our window, right? Our right pointer can't be over here, because if our right pointer was here, then our window is bigger than 3. So to do that, what we're going to do is shift our left pointer over here, and then this would be our new window. We're going to have a right pointer here, and then we're going to have it here. And then we're going to set our right pointer over here. These two aren't equal. Increment the right pointer. These two are equal, so we can return true. So that's essentially what I'm doing here. I'm going to set our right pointer over here. We've gotten to the end of our window, right? Our values in this window. And to do that, we're going to have a right pointer. So here our right pointer is going to be at this position. We're going to check, are these two equal? Nope. And then we're going to increment our right pointer here. Are these two equal? Nope. Well, we've gotten to the end of our window, right? Our right pointer can't be over here, because if our right pointer was here, then our window is bigger than 3. So to do that, what we're going to do is shift our left pointer over here, and then this would be our new window. We're going to have the right pointer here, and then we're going to have it here. And then we're going to set our right pointer over here. These two aren't equal. Increment the right pointer. These two are equal, so we can return true. So that's essentially what I'm doing here. We have nested for loops. The outer loop is going to run as many times as how many elements we have in the array, which let's say is n. The inner loop is going to run roughly k times, technically k minus 1, but we still say it's k just for simplicity. K is a variable. It could be anything. It's safe to say that the k is going to be less than or equal to n, because we can't have a window that's larger than the array itself. But that would mean our time complexity is going to be n times k. Now for small k values, for small windows, that's not too bad. But for large windows, it could be worse. And really quickly, if you're confused by this line over here, this can be a sort of common technique with sliding window problems. We know that for every value here, we want to check, is it equal to any other values that go in the same window, and do that for every single value. By the time we get here, we have our window ending at the perfect spot. Well, in this case, we would check, is 2 equal to 3? Nope. Is 2 equal to 3? Nope. And then we would want to still start our left pointer over here. Even though we don't have enough values to create a window of size k, it's okay if we have a window that's smaller than k. So this window is still valid, even though it only has 2 elements. Then we would check, is this left value equal to the right value over here? Yes, it is, so we would return true. When I iterate my right pointer, starting at left plus 1, going up until the minimum of the length and the minimum of left plus k, I'm saying, in this case, the length would have us stop here. The left plus k would have us stop at one element after that. But we know we don't want to end up going out of bounds, so we take the minimum of this and this, which would have us stop over here. So then we won't go out of bounds. That's what I'm doing with this line of code. But of course, it's not as efficient as we can have it, and what we're trying to do here is detect duplicates within a window. Detecting duplicates is something that can be improved with hashing. So we're actually going to use a hash set to optimize this to give us an optimized sliding window solution. And we could optimize it like this using a hash set to check for duplicates. Instead of having to manually compare every single element in the array to every single other possible value that could be in the same window, we can keep a rolling hash set of our window. Meaning that if this is our window, and we're going to continue to assume that, let's say k equals 3, if this is our window, then all 3 of these values will be added to the hash set. And as we go to the next position, because we just have a single loop here, we're iterating through every single position. That's our right pointer. By the time our right pointer gets over here, our left pointer is still going to be at 0. So what are we going to do? Because we've gotten to a point now where our window, or at least the pointers representing our window, are greater than the k value. That's this line of code over here. So what we're going to do is take the left value and remove it from our window, from our hash set, and then take our left pointer and then increment it to be over here. And so then this is what our new window is going to be looking like. First though, before we add this to the hash set, we're going to check, does this value already exist in the hash set? And that is a constant time operation. Instead of having this value and comparing it to this and comparing it to this and doing that for every window with every single value, we can do this in constant time with a hash set operation. In this case, 2 already exists in the hash set, so we can return true. Now if it didn't, we would simply add this to the hash set and then continue the algorithm. We would then add this value, pop this guy, increment our left pointer to be over here, and then this would be the new window, and we would keep going just like that. And we would even get to the small window cases where we have a window of size 2, we have a window of size 1, until we get to the end of the array. And if we never found a window that contained duplicates, we would end up returning false. This is the relatively simple sliding window case where we have a window of fixed size. But we know that's not always going to be the case. As we saw with Cadane's algorithm, the sliding window variation, our window could be of variable length, right? We showed a case where we had a window with 1, then 2, then 3, then 4, and then it skipped. We removed all these and then we had a window of 1 again. So that's what we're going to be focusing on next. Now let's take a deeper look. Duplicates is something that can be improved with check for duplicates. Instead of having to manually compare every single element in the array to every single other possible value that could be in the same window, we can keep a rolling hash set of our window. Meaning that if this is our window, and we're going to continue to assume that, let's say k equals 3, if this is our window, then all 3 of these values will be added to the hash set. And as we go to the next position, because we just have a single loop here, we're iterating through every single position, that's our right pointer. By the time our right pointer gets over here, our left pointer is still going to be at 0. So what are we going to do? Because we've gotten to a point now where our window, or at least the pointers representing our window, are greater than the k value. That's this line of code over here. So what we're going to do is take the left value and remove it from our window, from our hash set, and then take our left pointer and then increment it to be over here. And so then this is what our new window is going to be looking like. First though, before we add this to the hash set, we're going to check, does this value already exist in the hash set? And that is a constant time operation. Instead of having this value and comparing it to this and comparing it to this and doing that for every window with every single value, we can do this in constant time with a hash set operation. In this case, 2 already exists in the hash set, so it's going out of bounds, so we take the minimum for duplicates. Instead of have a single loop here where integers representing our is take the left k. It's okay if large windows, it could position, that's our right pointer. By the time our right pointer gets over here, our left pointer is still going to be at 0. So what are we going to do? Because we've gotten to a point now where our window, or at least the pointers representing our window, are greater than the k value. That's this line of code over here. So what we're going to do is take the left value and remove it from our window, from our hash set, and then take our left pointer and then increment it to be over here. And so then this is what our new window is going to be looking like. First though, before we add this to the hash set, we're going to check, does this value already exist in the hash set? And that is a constant time operation. Instead of having this value and comparing it to this and comparing it to this and doing that for every window with every single value, we can do this in constant time with a hash set operation. In this case, 2 already exists in the hash set, so we can return true. Now if it didn't, we would simply add this to the hash set and then continue the algorithm. We would then add this value, pop this guy, increment our left pointer to be over here, and then this would be the new window, and we would keep going just like that. And we would even get to the small window cases where we have a window of size 2, we have a window of size 1, until we get to the end of the array. And if we never found a window that contained duplicates, we would end up returning false. This is the relatively simple sliding window case where we have a window of fixed size. But we know that's not always going to be the case. As we saw with Cadane's algorithm, the sliding window variation, our window could be a variable length, where we showed a case where we had a window with 1, then 2, then 3, then 4, and then it skipped. We removed all these and then we had a window of 1 again. So that's what we're going to be size. But we know that's not always going to be the case. As we saw with Cadane's algorithm, the sliding window variation, our window could be a variable length, right? We showed a case where we had a window with 1, then 2, then 3, then 4, and then it skipped. We removed all these and then we had a window of 1 again. So that's what we're going to be focusing on next. So now let's look at sliding window problems where we need a variable length window. And let's take a look at a really simple example. We're given some input array of numbers. We want to find the length of the longest subarray that has the same value in each position. So essentially we're looking for the longest string of duplicates. Here we just have a single 4. There's no duplicates next to it. Here we have 2 2s, and here we have 3 3s. Of course the longest window is this one. Now the simple way to solve this problem with a sliding window would be to initialize the left and right pointers. In this case, they can be at the same position because this is a valid window. And then we would increment the right pointer. Now at this point, we would see that the right pointer is not equal to the same value as the left pointer. So that's a problem. We want our window to have the same value in every position. So what we should do is increment our left pointer until it's equal to the same value as the one at the right pointer. In this case, we only have to increment the left pointer once because then it'll be at the same position as the right pointer, and of course then they are the same value. And then we would increment our right pointer again, and now it's here. It's the same value as the one at the left pointer, so this is a valid window. And by the way, we're going to be keeping track of the length of the longest window. Before, the longest window was of length 1. Now we found one that's of length 2. So now again, we're going to increment our right pointer over here now. This is our window. Is it valid? Well, this value is not the same as this value. So this is not a valid window. We need to make it valid again. What should we do? Well, like I said, we want to increment the left pointer until the left value and the right value are equal. So now the left pointer would be over here, but these two values are still not equal. So our window is going to continue to slide. In this case, these two values were chopped off, and this is the new window. So now that our left pointer is over here, this is our window. It's of length 1. It's definitely not the longest because we earlier saw a window of length 2. But now we're going to once again increment our right pointer. Now it's over here. These two values are the same. This is a valid window of length 2. Now we're going to increment the right pointer again. These are the same, so this is a window of length 3. And that is the longest that we've seen so far. And then we would once again increment our right pointer, but now it's out of bounds. That's how you know we can stop. So what we would return as the longest length would be 3 in this case. And the code for that would look something like this, where we initialize our longest length to be 0, and we set our left pointer initially here, and our right pointer we could initialize to 0, but since we're iterating through the entire array with a for loop, we pretty much get that anyway. And what we're trying to do here is take our window and keep increasing it until we get to a point where we can't grow it anymore, and at that point we would start shrinking our window from the left side. But actually, what I didn't show when we were walking through the example is, when we were at this point, we had a valid window. Then we found a new value that was not equal to the one over here. We actually don't need to take the left pointer and increment it by 1, because we know that if we just found a new value here, that all the other values here were duplicates. So instead of taking this left pointer and incrementing it by 1, we can immediately set it to the right pointer. And that's what we do in the code. It doesn't really change the time complexity. It's just that this is such a simple problem that we don't need an inner loop. But I'll touch on that in the next example. And on every iteration, we calculate the length of the window. So if this was our window over here, we know that this is index 0, this is 1, 2, 3. The size of our window is 3. We can calculate that by taking the right pointer, subtracting the left pointer, which gives us 2, and then we add 1 to it. That's just how we calculate the length of this window. Because we got a result of 2, we know that's not the case. This window is of length 3, that's why we have to add that 1. And this problem is actually simple enough that we don't really need the sliding window. At least we don't explicitly need a left and right pointer. I'm just doing this to kind of show you the main idea behind the sliding window. I encourage you to try to rewrite this solution without even using left and right pointers. If you get stuck, feel free to post your code in the Discord. But now let's look at a more complicated sliding window problem. Now, given an array of all positive integers, we want to find the minimum length subarray where the sum is greater than or equal to some target value that we're given. And given a problem like this one, you would want to pay special attention to the fact that all values in the array are positive. When you're given a detail like that in an interview question, it's usually not arbitrary, unless you have like a really evil interviewer who is just trying to trick you. Usually a detail like this indicates something, and it's sort of a hint at what the solution could be. And in this case, we're trying to find the length of the subarray itself. In this example, let's say the target is equal to 6. Now, the obvious brute force solution would be to go through every single subarray and find all of the subarrays that total up to 6, and then among those subarrays, keep track of which one had the minimum length. So running through that quickly, it would look like this. This is one subarray, it's smaller than 6. Let's add another value to it. This is 5, it's still smaller than 6. Let's add another value to it, 6. It's exactly equal to the target. Well, what's the length of this subarray? We would just get the beginning and the ending index and easily calculate it. The window is of size 3, so that's our minimum length so far. Now, paying attention to the fact that all values in this array are positive, we can continue to grow our window. Our window is starting over here. This is the left pointer. We can continue to increment our right pointer and grow this window. But let me ask you something. Starting from here, are we ever going to find a window that is smaller than length 3 that satisfies this condition? Definitely not, because all these values are positive. We already have a window that sums up to the target 6. By adding more values, the window is going to grow larger and larger. It's not going to ever get smaller. We're never going to reach the target starting from here. So at this point, we know we have to shrink our window for us to ever get another valid window. So what we're going to say is, starting from here, what's the minimum length window that would sum up to the target 6? So what we would do is take our left pointer and then increment it. And after we've done that, we can go to the next iteration of the loop, where our right pointer now is going to be shifted over here. And this is the next value that we're adding to our sum. By the way, when we shifted our left pointer, our sum was 6. But when we remove this value from the window, we take that value, which was a 2, and then decrement it from our window. So now our window is a sum of 4. Notice how we didn't have to go through every value to recalculate that. We were keeping track of the total sum. When we remove one value, we can just decrement it from the total sum. And now that we're going to another value and adding it to the window, we're going to simply add that 2 to our total sum. So our total sum is now 6. Once again, we reached the target, but the window is of exactly the same length. So our minimum window length is still 3 for now. But once again, we're going to shift our left pointer by 1 to be over here now. And now our window sum was 6, but we removed a 3, so now our window sum is equal to 3. So now once again, we're going to go to the next iteration of the loop, where our right pointer is going to be incremented. So our sum is 3, but we're adding a 4 to our window. So now our sum is going to be 3 plus 4, which is equal to 7. So that is not equal to the target, but it's okay, because we're only looking for sums that are greater than or equal to the target. So this is technically a valid window. But we want to find the smallest window possible, which is exactly why we're going to now take our left pointer and then increment it, but we're not necessarily only going to do it once. Right now we just removed a 1, so therefore our total sum is now going to be 6, and our left pointer is going to be over here. This is also a valid window. The sum is 6, our target is 6, and now this is actually the new minimum window. It's of length 2. But since the sum is still greater than or equal to the target, we're going to keep shrinking this window. We're going to take the left pointer and once again increment it. Now it's going to be in the same position as the right pointer, and our sum is now going to be 6 minus 2, which is going to be 4. So now this window is no longer valid. And things have gotten a little messy, so I'm going to clean it up a little bit. So our left pointer would be all the way over here, same as the right pointer, and then we would now increment the right pointer one more time, and this would be the new window. The sum would now be 7, it's greater than or equal to the target, so this is a valid window. It's of length 2, which was the same minimum length that we calculated earlier. So now we would try to increment our left pointer, remove this, so 7 minus 4, our sum is 3 now. This is our window, and it's no longer valid. So then we would try to increment our right pointer again, it's out of bounds. So that's how you know we can stop. So now let's take a look at the code, and I'm going to explain to you why the time complexity is still big O of n. So we initialize our left pointer all the way at the beginning. As with most sliding window problems, our total is initially going to be 0. You could also call that our current sum, like our window sum. Our length is initially going to be positive infinity because we're trying to minimize it. So by setting it to a really big value, when we run our min function, we will end up reducing it. You could also initialize the length to be the length of the input array plus 1. That would also be a good default value. And let's assume that in this example, if we never find a window that has a sum of greater than or equal to the target, we end up returning 0. And we would know that because our length would still be the default value that we set it to, which in this case is positive infinity. So if that was the case, we would return 0, as us indicating we could not find a subarray. But if we do find a subarray, we return the length of it. Now the code isn't super crazy. We have our left pointer. As we take our right pointer and keep shifting it, we're adding that value to the total current sum. If the current sum ever is greater than or equal to the target, that means we have a valid window. So the first thing we're going to do is take the length of that window and check, is it smaller than the current length that we've calculated so far, the current minimum length? If it is, we reassign the current minimum length. That's step 1. Step 2 is where we try to shrink our window. That means we take the left value over here and subtract that from our total, just like I was doing earlier. Here, our total would be 6, so we're going to subtract 2 from it, and now it's going to be 4. We're also going to take that left pointer and then increment it by 1 to be over here. So we're going to continue to do this until our window is no longer valid. The reason we're doing it is because, remember, our goal here is to find the minimum length subarray. So as we keep shrinking the window from the left, we're finding the smallest possible subarray. And the rest of this walkthrough would play out just like we talked about a second ago. So this sliding window solution is a linear time algorithm, but the code can be confusing because normally when we have nested for loops, we're kind of trained to think that that is an n-squared solution, but in this case, it's not. Let me explain to you exactly why. We have an outer loop. We know for sure that the right pointer is going to visit every single position in the input array. We also know that the left pointer is possibly going to visit every position. It's going to start at the beginning, and it's going to be incremented in some cases when the inner while loop runs. But the left pointer might not necessarily reach the end of the array. Let's suppose that in this case, our target was actually a really big value, like 6. So in that case, our left pointer would start here, and the inner loop would never run because our total would never be greater than the target. But in the worst case, as we showed a second ago, when our target is 6, our left pointer would have been in this position, and in this position, and in this, and all of these. So what I'm saying here is that looking at this, it's clear that the time complexity is roughly 2 times n, which we know reduces to big O of n. So how can that be possible when we have an inner loop? Well, the thing with this inner loop is it's not always going to execute. When our right pointer is over here, our left pointer is still going to be over here. When our right pointer is over here, our left pointer is not going to be changed. It's going to stay exactly where it is. When our right pointer is over here, our left pointer is going to be incremented once because our total sum was equal to the target. So we had to shrink the window, so then we move it over here. When our right pointer is over here, once again, our sum was equal to the target, so we increment the left pointer and move it over here. When our right pointer was over here, our sum was once again greater than or equal to the target, so we incremented our left pointer once, and then actually it was still greater than or equal to the target, so we incremented our left pointer twice. What we're starting to notice is, in some cases, the inner loop ran once. In other cases, like over here, the inner loop never ran, and in some cases, like over here, the inner loop ran multiple times. Finally, when we're finished, when we get to this point, our left pointer was once again shifted by 1, but our left pointer was still shifted only n times. That means the inner loop runs a total of n times. Not n times for each iteration of the outer loop, but n times total. I hope this makes it clear why even though we have an inner loop, the time complexity is still big O of n. It's about the total number of times that the inner loop is going to execute. And as I just showed, it's only going to execute a total of n times. So this is the general pattern and generally what the code looks like when you have a sliding window solution where the window is a variable length. You usually have an inner while loop, but that doesn't mean the time complexity is worse than big O of n. So then this is what our new window is going to be looking like. First though, before we add this to the hash set, we're going to check, does this value already exist in the hash set? And that is a constant. Next, let's move on to two-pointers, and we've technically already been talking about two-pointers in many of the algorithms we talked about. That's because two-pointers is a very, very large and general topic. Sliding window is pretty much a subset of two-pointer problems. You might be wondering, what exactly is a sliding window problem compared to two-pointers? Like, what's the exact distinction? Well, generally speaking, with two-pointer algorithms, we care mostly about the two individual elements that the pointers are pointing at. But as we saw with sliding window, we care about the entire window. It could mean, we care about every unique value that's in this window, or we care about the total sum of all values within the window. That's generally the distinction, but I don't think it's a huge one. In my opinion, two-pointers and sliding window are two sides of the same coin. But now let's look at a really, really simple example. Given some array or some string, let's check if it's a palindrome. Arrays are essentially strings, so we don't really care too much whether we're looking at integers or we're looking at some character or something else. We just want to know if it's a palindrome. A palindrome is something that once you reverse it, it's the same thing. So if we were to reverse this, we would get 1, then we would get 2 over here, and continuing, we would get something like this after reversing it. It looks the exact same as the original, so therefore it is a palindrome. So we could solve this problem multiple ways. We could, build another array by iterating through these elements in reverse. But an easier way is with two pointers, because then we don't need extra space. We initialize a pointer all the way at the left and a pointer all the way at the right, individual elements that are pointing at. But as we saw with sliding window, we care about the entire window. It could mean, we care about every unique value that's in this window, or we care about the total sum of all values within the window. That's generally the distinction, but I don't think it's a huge one. In my opinion, two pointers and sliding window are two sides of the same coin. But now let's look at a really, really simple example. Given some array or some string, let's check if it's a palindrome. Arrays are essentially strings, so we don't really care too much whether we're looking at integers or we're looking at some character or something else. We just want to know if it's a palindrome. A palindrome is something that once you reverse it, it's the same thing. So if we were to reverse this, we would get 1, then we would get 2 over here, and continuing, we would get something like this after reversing it. It looks the exact same as the original, so therefore it is a palindrome. So we could solve this problem multiple ways. We could, build another array by iterating through these elements in reverse. But an easier way is with two pointers, because then we don't need extra space. We initialize a pointer all the way at the left and a pointer all the way at the right. We compare the two individual elements at each pointer. We call these the left and right pointers. If they're equal, then we increment the left pointer and we decrement the right pointer because we want to shift it this way, and we keep comparing these values. Now, what if this 2 was actually a 3? Then we would see that this is not equal to this, therefore we would return false. It's not a palindrome. But in this case, it is equal, so we would continue. We would increment our left pointer here now, and then increment the right pointer here. These two are also equal, and at this point our left pointer would be incremented here, and our right pointer would be decremented over here. But since they've crossed each other, we know we can stop. I mean, we could keep checking if we wanted to, but we already know that these two values are equal. So by having the right pointer here and the left pointer here, we're just making the exact same comparison. If we move the right pointer over here and the left pointer over here, then we would just be comparing these two again. We already did that. There's no need to do it again. So the code for that would look something like this. Suppose we're given some word or some array. It doesn't really matter. The algorithm will be the same either way. We initialize our left and right pointers at the beginning and the end. Now, while this is a really, really simple example, there are a lot of problems that follow this exact same pattern, where you initialize a pointer at the beginning and initialize another pointer at the end. In this case, we just compare the characters. If they're unequal, we return false. Otherwise, we shift the pointers. And if our pointers ever cross each other, that means we check every single pair of characters, and therefore the input is a palindrome, and we can return true. Now let's take a look at a more complicated example. Suppose we're given a sorted input array. As you might guess, that's going to be important for this problem. We want to return two indices of two separate elements, meaning that they have to be in different positions, which sum up to the target value. In this case, for this example, let's say the target value is equal to 7. And let's assume that there's always going to be exactly one solution. The obvious two-pointer solution would be the brute force one. We have two pointers, we compare every pair of elements to each other, we take every single pair of elements, add them together, and check if they're equal to the target. If they are, we return the indexes of those two values. And then, with -1, we would compare with this guy, then this guy, then this guy, then this guy, and keep doing that. That would be obviously an n-squared solution, because then we would have to do the same thing with this guy. Compare it with this, 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 and this. Well, not compare, but add it with that, and then check if it's equal to the target. but again, it's an n squared solution. Now the input array is sorted. So an easy thing to do would be to say, well, we know the largest element is going to be over here. How can 9, which is greater than the target, ever sum up with some value to be equal to 7? How would that even be possible? Can we just go ahead and say, this is definitely not going to be a part of the solution, and the same thing for 8? Well, we can't quite do that because, as you can see here, we have some negative values. So it technically is possible that this 9 added with a -2 would equal the target. In this case, though, we don't have a -2. So, initializing 2 pointers the same way we did earlier, do we have any information? This is our largest value, and this is our smallest value. We add them together, we get 8. That's bigger than the target. So what does that tell us? When we took the largest value and added it with the smallest value, we were still larger than the target value. That means that there's no possible element in the entire input array that we could add to 9 that would equal the target, because we tried the smallest value and that still didn't work. So that tells us that 9 is never going to be part of a solution. So we would never consider 9. So in this case, we would shift our pointer over here. Since we know our array is sorted, this value is going to be less than or equal to the value over here. So we have to check now if we have a solution. We had -1 and +8. That's exactly equal to the target, so we found it. But to make this a bit more complicated, let's assume that this was actually a positive 7. In that case, we would add 7 and -1. That would be 6. So at that point, we would say our sum is smaller than the target. What does that tell us? Well, first of all, we know for sure that this 9 could never be part of a solution. We talked about why earlier. At this point, do we know for sure that one of these values can never be part of a solution? Well, this is the smallest value we have, and we added it with the biggest value available to us, except for this one, of course, but we added it with the 7, and it was 6. It was still too small. So since the remaining values over here are going to be less than or equal to the 7, there's no possible value remaining in the array that we could add to -1 that would equal 7. It's just impossible. That's math. These values are less than or equal to 7, so therefore nothing we add to -1 is going to be equal to 7. So therefore, we know for sure that this -1 is never going to be part of a solution. So very simply, we take our left pointer and we increment it by 1 to be over here now. At this point, I think we're ready to take a look at the code. We initialized our left and right pointers at the edges of the input array, and we're continuing the algorithm until our pointers meet or cross each other. We're guaranteed that there's a solution, so we know that this loop is actually never going to exit, so we don't even have to return anything outside of it. We know we're going to find a solution. But before we find a solution, when we have our total sum, and the total sum is larger than the target, as when we initialize our pointers here, then we take the right pointer and decrement it. We know the input array is in sorted order, and by taking the right pointer and decrementing it, we're decreasing our sum. So that gives us a chance. Since our sum was too big, let's decrease it. If our sum is too small, let's increase it. So as we saw a second ago, when our left pointer was over here, we had -1 plus 7. That was 6. That was too small. So we took our left pointer and incremented it to see if we could find a solution. By increasing our sum, maybe we'll get closer to the target. So now our sum is 2 plus 7. That's still too big. Our sum is 9. So once again, we're going to take our right pointer and decrement it. Now the right pointer is going to be over here. We did that because we know for sure that this 7 is never going to be part of the solution, because all the remaining elements are going to be greater than or equal to 2, and if 2 plus 7 was still greater than the target, which is 7, then there's no other element here that we can add to 7 that would be equal to the target. Now we have 2 plus 4. That's smaller than the target, so we're going to take our left pointer and increment it to now be in this position. Well, this is the last possibility we have, so it better be the solution, and in this case it is 3 plus 4 is equal to 7, so then we would return the indices of those two elements. I think it's pretty clear why this algorithm is big O of n, because we initialize our pointers, and in the worst case, as we just saw, we would have pointers and we'd keep shifting them until they basically met each other. That would mean we looked at every single position in the input array. So this is a 2-pointer problem, and it's definitely not a sliding window. I kind of call this the shrinking window, because this is a pattern you see pretty often where you initialize 2 pointers at the end, and then you start moving the pointers towards each other based on some kind of conditional logic. But nobody else really calls this the shrinking window, at least not that I've seen. Now let's talk about a pattern that comes up a lot when it comes to arrays, and that is prefix sums. Prefix sums actually aren't super complicated, and they usually don't require any super crazy data structures or algorithms. The idea is that if we have some array, a prefix sum is defined as being, first of all, let's talk about the word prefix here. A prefix basically means that we're starting at the beginning, so a prefix. So a prefix of this array is any subarray, any contiguous subarray typically, that starts at the beginning of this array. So this is one prefix of the array. Another prefix would be the first 2 elements, and then we can add another, and now this is a prefix, and then add another, and this is a prefix, and this is a prefix. The entire array itself is technically a prefix of itself. Now, this is not a prefix because it does not start at the beginning, and this is not a prefix usually because while it starts at the beginning, it's not contiguous. Typically, prefixes are contiguous blocks that start at the beginning. And typically with prefixes, now extending that, a prefix sum would basically be any prefix of this array. It would basically mean for any prefix of this array, we also calculate the sum of that prefix. And you'll see why we do that and why it can be helpful and make things more efficient. So this prefix sum would just be 2. This prefix sum would be 2 minus 1, which is 1. And now there's a bit of repeated work actually, because if the prefix sum of this is 2, the prefix sum of the first 2 values is 1, how do we get the prefix sum of the first 3 values? Well, we already know the prefix sum of this, and then we add 3 to it. So we take 1 plus 3, and we get 4. Now to get the prefix sum of the first 4 values, we can take 4 minus 3, which is going to give us 1. To get the prefix sum of the entire array, we can get 1 plus 4, that's going to be 5. Now, even though we're talking about prefix sums, generally under this pattern, you could do other things. Another common thing is prefix products. So what we did was the sums, but you can also calculate the product. So for this prefix, the product would still be 2. For this prefix, the product would be 2 times -1, that'd be -2. The product for the first 3 values would be -2 times 3, that'd be -6, and etc., etc. You could do that, and sometimes that's also a pattern. The main thing that we're worrying about here is the commonality between that is that it's a prefix. Now, there's also another thing called postfix, which is sort of the opposite of a prefix. With prefixes, we have every subarray starting at the beginning. A postfix would be every subarray starting at the end. So this would be a postfix, this would be a postfix, this would be a postfix, etc., etc. Basically, prefixes and postfixes are 2 sides of the same coin. Because generally we use prefixes to eliminate repeated work. Let me show you what I mean. The classic problem with prefixes is that we're given an array of values, so that this would be our array in this case. We want to design a data structure that can query the sum of a subarray of values. That sounds more complicated than it is. Basically, that means that we could call some function called maybe query sum, pass in 2 indices left and right. So maybe in this case, this is our left and this is our right, and this function could calculate the sum of this subarray. Now, the naive way to implement a data structure that could do that is basically not worry about prefixes, just have an array given 2 indices. It's pretty easy to calculate the sum of that subarray. Just go through every position, add it to some total, and then return that total. So while this is an easy problem to solve, it can be done more efficiently, because the naive way to do it would be, in the worst case, an end time operation every time we call query sum. But using prefix sums, we can actually eliminate pretty much all of the repeated work. Let me show you how. Now, while none of our prefix sums that we calculated will give us this calculation that we want, and that's expected because we have an array of, let's say, n values, the number of subarrays we could have is n squared, right? We could have, this subarray, this subarray, this subarray, right? These are prefix subarrays, but we could have other subarrays like that, like this. And our prefix sums only tell us the sums of every subarray that starts at the beginning. They don't tell us the sums of these. We haven't pre-computed that, but we don't need to actually, because while we're looking for this sum, we can get pretty close with this value. This value will tell us the sum of all of these values, right? So that's what we want, except we want to chop off this value. So how do we do that? Well, we take the prefix sum of all these, which is this, subtract from it the prefix sum of all of these values, and there was only 1 in this case, so we take 1 minus 2, and then we would know that the sum of this subarray is 1 minus 2, which is -1. And when you just look at the values individually, 3 minus 1, that's going to be -1. So that is the case here. Doing the exact same thing for this subarray, we would want the prefix sum of the array up until this point, which is 5. But we'd also want to remove this prefix sum, the prefix sum of these 3 values. So we would take 5 minus 4, because we know 4 represents the prefix sum of these values. So 5 minus 4 is going to be 1, and looking at the values individually, that is the case. The sum of this subarray is indeed 1. Now, because we pre-computed these prefix sums, every time we're given any arbitrary subarray, we can get the prefix sum in all at one time, because we're just doing a single calculation. We're taking some value, subtracting another value, and that gives us the sum of that prefix. So this is one of the most classic prefix sum problems. There are many others just like this problem that kind of use a similar idea of pre-computing work using prefix sums, and then that makes additional work that we need to do a lot easier. Now, I also mentioned that prefix sums and postfix sums are just 2 sides of the same coin, and the reason is because we could solve this problem the exact same way using postfix sums instead of prefix sums. Maybe you can even think of how we could do that, assuming that the values that we computed here were actually postfix sums and not prefix. That means that the value here would represent the sum of this subarray, and the value here would represent the sum of this subarray, the value here would represent the sum of this subarray, etc., etc. Then, if we wanted the sum of this subarray, we would just take this value, which would represent this sum, and then subtract from it this value, which would represent this sum. That's why postfix sums are pretty similar to prefix sums. But now let's take a look at the code. So the code for our data structure could look something like this, where our constructor is given some array of values. Let's assume we're only given a single array of values, and that's it. We're not going to be given a new array every single time, so that when we pre-compute the work, that we don't have to continuously do that. We only have to pre-compute the prefix sums a single time. So given some array of nums like this one, we're going to initialize our data structure by computing the prefix sums just like we have shown over here. So we'll have a member variable array called prefix. We'll keep track of our total, because calculating the prefix sums is pretty easy. Initially, our total is going to be 0. We're going to go through every number, so 2, and then we're going to add that number to our total. So our prefix sum so far is 2. And then we're going to append that to the prefix array. Then we're going to get the next value, which is -1. We're going to add that to our total so far, and that's going to total to be 1. We're going to add that to our prefix sum array, and we're going to just keep doing it. 3 plus 1 is going to be 4, and then negative 3 plus 4 is going to be 1, and then 4 plus 1 is going to be 5. So we only do that once. Now when we want to calculate the range sum of any subarray, we can do it in constant time. Because we did the pre-work here, we did an O of n work to initialize the prefix sums, and now we can do the range sums a lot quicker. If we solved this problem without prefix sums, we just had a single array, our constructor would have been efficient, because all we would have done is just copy nums into like a member variable. For that would have been a constant time operation. But our range sum would have been a linear time operation. And assuming that we're going to be calling range sum very frequently, and we're not going to be calling the constructor very frequently, that's why solving this with prefix sums is more efficient, because we're assuming that range sum is going to be called more frequently. Now range sum is not super complicated, so assuming our left and right indices were this, and assuming our left and right indices were this for one call to this, we would want the prefix sum, like the range sum of any subarray, we can do it in constant time. Because we did the pre-work here, we did an O of n work to initialize the prefix sums, and now we can do the range sums a lot quicker. If we solved this problem without prefix sums, we just had a single array, our constructor would have been efficient, because all we would have done is just copy, do the range sums a lot quicker. If we solved this problem without prefix sums, we just had a single array, our constructor would have been efficient, because all we would have done is just copy nums into like a member variable. For that would have been a constant time operation. But our range sum would have been a linear time operation. And assuming that we're going to be calling range sum very frequently, and we're not going to be calling the constructor very frequently, that's why solving this with prefix sums is more efficient, because we're assuming that range sum is going to be called more frequently. Now range sum is not super complicated, so assuming our left and right indices were this, and assuming our left and right indices were this for one call to this, we would want the prefix sum of the right portion, so where our right pointer ends, we'd want the total sum of this, which we could just get from this index. So that's exactly what we're doing here. We're taking the right index and getting the value from our prefix sum array. So this is the right prefix. So this is the right prefix sum. We also want the left prefix sum, which is just as easy. We just take the value at the left index of our prefix sum array. But what about the case where we're computing this prefix sum? And then we'd also want to remove the prefix sum of all values to the left of our left pointer. So that is just as easy, because we would just take the prefix sum of left minus 1. So you can see that over here. But there's one catch, because what if we were computing this range sum? Well, in that case, the left minus 1 index is out of bounds. We definitely don't want to go out of bounds. There's nothing there for our prefix sum anyway. So how would we calculate the sum of this subarray anyway? Well, we know that this value here would represent this sum, and we would go left minus 1 over here and then subtract that value, but that's out of bounds. So what should the default value be over here that we want to subtract from our total? Well, the default value should just be 0, right? Because we don't want to subtract anything from this sum. This sum tells us the value that we want to return, right? But this value tells us the prefix sum, which is the sum of our subarray. So what we say is, over here, I do this with a ternary operator, but you can actually have like a full if-else statement if you want. I just think this is shorter, and this works in most languages with a ternary operator. But we want to do this if our left pointer is greater than 0. But if our left pointer is equal to 0 exactly at that 0 index, then we want to set this to a default value of 0. And then once we have that, we simply take the right prefix sum. So for this example, that would be this value, and subtract from it the left prefix, which would be this value. So that would tell us this sum. Subtracting this sum would give us 0, because 1 minus 1 is 0, and that's what the sum of this subarray is. So that's how we would do it. So I think this is one of the patterns that isn't super crazy, especially once you get familiar with it. It comes up a lot. This is definitely one of the most common patterns when it comes to data structures in general, even in coding interviews, and luckily it's not super crazy. So I definitely recommend practicing this pattern. There's a ton of problems that can be solved using prefix sums or postfix sums, or sometimes prefixes without sums. Maybe it'll be a product or something else. It's a pretty open-ended pattern. Next, let's look at another two-pointer algorithm. This time, usually it's used for linked lists. It's called the fast and slow pointer algorithm. It can also be called Floyd's tortoise and hare algorithm. The tortoise is essentially the slow pointer, and the hare is the fast pointer. It can be used for a lot of things. The first example we're going to look at is pretty trivial. It's finding the middle of a linked list, which can actually be accomplished without this algorithm. The easiest way to determine the middle of a linked list would be to, count the length. So 1, 2, 3, 4, 5. So we have the length, and then we would find the midway point. When we have a linked list that's odd length, it's pretty straightforward what the midway point is here. But what if we actually had a linked list of even length? What would we define the middle? Well, we have two middle nodes. We could say this is the middle, or that's the middle. Let's say that for this question, we assume this is the middle node. So of the two middle nodes with a linked list that's even length, we would take the second one and say it's the middle. So by calculating the length, we can also solve this problem in O of n time. We just have to iterate through the linked list, find the length, then start at the beginning again, and then iterate through half the list, and then we would find the midway point. That's a linear time algorithm. Now, this two-pointer technique, fast and slow pointer, is also going to be a linear time algorithm. So there's no improvements with this algorithm, but I think it's important to understand because it can be applied in many many different areas, which we're going to talk about here. The idea is that we have 2 pointers, a fast pointer and a slow pointer. We initialize them at the head of the linked list. Now on each iteration of the loop, we're going to take this fast pointer and shift it by 2 spaces. That's why it's the fast pointer. The slow pointer is going to be shifted by 1 space each time. That's why it's the slow pointer. The fast pointer is clearly twice as fast as the slow pointer. We're going to keep doing this until one of the pointers reaches the end of the linked list. Now it's no surprise that the fast pointer is going to reach the end before the slow pointer. So again, here the fast pointer is going to be incremented by 2 positions, and the slow pointer is going to be incremented by 1. When we say reach the end of the linked list, that means the fast pointer is either at the last node in the linked list, or it's equal to null. So in this case, we would say the fast pointer is at the end of the linked list. Now, you tell me, if the fast pointer traveled the entire length of the linked list, how far did the slow pointer travel, given that it's traveling half as fast as the fast pointer? Well, the slow pointer would have traveled half the length of the linked list. That means by the time the fast pointer reaches the end of the linked list, the slow pointer should be at the middle of the linked list. And you can see it works out perfectly, at least when we have a linked list that's of...
Okay guys, I hope you learned a lot. Today we did some practice questions on neat code, arrays. Now we're into the linked list one. But yeah, we didn't get to finish because 1 minute left on this, and I'm gonna go walk and bathe and all that stuff. I mean, finish walking, bathe and all that stuff. As you can see today, I had a lot of breaks in terms of walking. Tired, just from body, so I have to match my body out, you know. It's been too much, but we still push, right? So I'm at 25. This is day 25. 5 more days to go. 5 more days to go. Yeah. Now I just did that at 3.4 miles per hour for the whole time. That's like 6K. And 10 seconds left. Leave up yourselves. Keep staying amazing. Amazing. I'm out.